whether voice is. Yes, sir. Thanks for joining, sir.
Good morning, sir.
We'll start after just 5 minutes, sir.
Sure. Please take your time.
A very good morning to everyone. Dear participants, we'll start the session in another 5 minutes. Very good morning to all. I, Vaishnavi Dia, Assistant Professor in the Department of Civil Engineering, deem it an honor to welcome all the faculty participants for the second day of our faculty development program on sustainable construction materials, practices and technologies, organized by Department of Civil Engineering, Sir MVAT. Now, I would like to take this opportunity to extend a warm welcome to our guest speaker, Dr. K.S. Nanjunda Rao, Chief Research Scientist, IISc, Bangalore. Welcome you, sir.
Thank you.
Now, I request our HOD, Dr. Ravikumar H, to address a few words about today's session. Over to you, sir.
Dear participants, a very good morning to one and all. We welcome you for the second day faculty development program focusing on sustainable construction materials, practices, and in a word, for us, latest advancement in sustainable construction program. We will try to explore innovative materials, business technologies that are not only minimize the environment footprint, but also enhance the longevity and durability of our industry and environment. Let us dwell into the critical topics together, empowering ourselves to lead the way towards a more sustainable future in construction. Today, we are going to have a session on Earth as a building material, history, properties, and engineering behavior by Dr. K.S. Nanjun Rao from Indian Institute of Science, sir. Now, I request Ms. Bhavya to introduce the speaker of the day.
Yes, sir. Okay, a very good morning to all of you. I, Bhavya S., Assistant Professor, Department of Civil Engineering, Sir MVIT. It's my honor and privilege to extend a warm welcome to our esteemed guest speaker, Dr. K.S. Nanjunda Rao, Chief Research Scientist in the Department of Civil Engineering at the prestigious Indian Institute of Science, Bangalore. Dr. Nanjunda Rao's academic journey is a testament to his dedication and passion for civil engineering. Having earned his bachelor's and master's degree in civil engineering from Bangalore University, he went on to achieve a pinnacle of academic excellence by obtaining his PhD from the Indian Institute of Science, Bangalore. His expertise spans a wide array of fields within civil engineering, including mechanics of composite plate and shell structures, earthquake-resistant design, reinforced and pre-stretched concrete structures, and the applications of fiber-reinforced polymer in civil engineering projects. Dr. Nanjunda Rao's contribution to the field are not only the theoretical, but also practical, as evidenced by his numerous publications in reputable international journals and conferences. His groundbreaking work has not only expanded the boundaries of knowledge in civil engineering, but has also paved the way for more sustainable and resilient infrastructure solutions. Moreover, Dr. Nanjunda Rao's commitment to the excellence has been recognized through prestigious awards such as ACC Nagadi Award in 2008, acknowledging his outstanding publications titled Alternative Building Materials and Technologies. Behind academia, Dr. Nanjunda Rao has generously shared his expertise by serving his leadership role as a member of various technical committees constituted by the government of Karnataka and other premier organizations. His dedication, expertise, and scholarly achievements truly embody the spirit of academic excellence and service to society. We are indeed fortunate to have him with us today to share his insights and knowledge. Please join me in extending a warm welcome to Dr. K.S. Nanjunda Rao. Once again, welcome you, sir. Thank you.
Thank you for your kind words, madam.
Thank you, sir. Over to Vaishnavi.
Thank you, Bhavya. Now I request Dr. K.S. Nanjunda Rao, sir, to take over the session.
Sure. I'll start sharing my slides.
Yes, sir.
Yeah, can you give me the rights?
Right. So you can share.
Yeah.
Sir, you can share your screen now.
I'm doing, madam. Are you able to see my screen, please? My desktop is visible?
No, sir, not yet.
Okay. Let me go back. Again, let me see. What about now?
No, sir.
Now it may be visible, right? Hello?
No, sir. It's not.
Let me see what I should be doing. Share.
Yeah, sir.
Now my screen is.
Yeah, your desktop is visible.
Yeah. Now I'll start the presentation. Yeah, this
Yes,
first slide is seen, right?
Yeah, sir.
Okay, I'll put it in slide mode.
Yeah, sir.
Right. Yes, sir. Perfect.
Yeah. I think it's visible.
Yes, sir.
Okay, thank you. A good morning to all of you who are participating in this faculty development program organized by Sir MVIT. I sincerely thank the head of department and the Department of Civil Engineering, all colleagues, for giving me this opportunity to share my experience on this particular topic, which is titled today. Our discussion will be Earth as a building material. We look at its history, properties, what materials go up to make this particular material, and the engineering behavior of this material in the context of sustainability. So, as already mentioned, I am from the Department of Civil Engineering and Institute of Science. Currently, the NIT Surathkal invited me to serve as an adjunct professor. So, I am currently on leave from Indian Institute of Science, and I am the adjunct professor at Department of Civil Engineering, NIT Surathkal. Now, let me start with this slide. This is the sanctum sanctorium of my great institution, that is Indian Institute of Science. There are two reasons why I am showing you this slide. The first and foremost thing, even though people were talking about, not even coined the word sustainability, and people did not even know what is sustainability, it was practiced in many different ways, and this particular building is a demonstration of that. This was the entire idea of Indian Institute of Science was conceived by two great visionaries, Vivekananda and J.N. Tata, while they were going to Chicago. And that is when the discussion happened that we need to establish a research institute in India during the British times. And at the same time, Tata was also very much interested in starting a steel plant in this country because we were importing all the materials. So these discussions between these two great giants, visionaries, finally has given birth to this Indian Institute of Science. It took its birth possibly in 1903-4. And at the same time, I would like to recall and thank another great person when they were really scouting for land to establish this institute after the idea was mooted by J.N. Tata. And with great difficulties, the British agreed. They were looking for land, where to set up in which place. Initially, it was Roorkee, but subsequently, for great difficulties, they finally chose Bangalore for setting up this. And when this information that the Tata is looking for some land and he is interested in setting it up, information reached the Maharani. At that time, Krishnarajendra Odier was a very young person. Therefore, on his behalf, the Rani was actually ruling the uh, Mysore state, and she just took 5 minutes to give clearance. Just 5 minutes. Imagine today you take so many years to clear a proposal, and she just took 5 minutes and gave something like more than 600 acres of land, which is now the more or less the center of this Bangalore city. And at that time, they started constructing this. Is the first building, the main administrative complex today, what we call the tower building. This is the entire material which is used in this construction, the stones, were quarried locally. You can see near swimming pool of the Indian Institute of Science, there is a huge quarry, and local, that is use of local materials is one of the important things of sustainable construction, so that you don't have to waste a lot of energy in transporting, and use of local materials is a very important thing in sustainable construction. So this building is a standing example of the awareness of using local materials, and this gigantic building, which is close to 120 years now, maybe it completed in 1909, is still today a standing example of what a sustainable construction can do. And anyway, we will have to really maintain all these facilities, not just build. So coming back to the proper, which is Earth as a subject matter of today, this slide shows you two pictures. The picture on top, it is the global distribution of earthen construction. You can see the global distribution of the earthen construction, and the wherever earthen construction is there, I think I'll put my pointer. Hopefully, we should be able to see. See, you can see, I hope you are seeing the pointer. All these places, this is South America, this is North America. All these places, you have significantly large earthen constructions. This is Africa. Then you see this is the entire Asian continent, and you have India here. Lot of urban constructions in this. Now the picture below, she gives you the distribution of earthquake epicenters around the globe. Each dot in this is representing an earthquake, which very clearly shows several thousands of earthquakes have happened, and they are all concentrated in certain regions. And more so, they are wherever there is urban architecture, you see a lot of earthquake activity as well. The comparison between these two pictures very clearly shows that wherever there were urban architecture was practiced, they were all highly seismically active regions, and has numerous earthquakes that have occurred in these areas. And earth as a building material, is the first material. You can say it has a huge history. That is one of the materials which was locally available, and therefore it was employed in its raw state. And subsequently, as the development took place, as scientific progress took place, it is no longer in the raw state, but still people use it in the raw state. That is only earth without any stabilizing. Now, sustainability is what is the buzzword today. People simply use the word. Now, what is it? From among the challenges of the future, starting with the hot topic of recent economic blow-up, to the global socio-political scene, as well as the cultural needs for the growth of mankind, there is one which can be considered extremely fundamental for all future development, and that is sustainability. Now, let's look at what is the sustainability, loosely used word very often by everybody. What is sustainability? Can it still be a buzzword? But what does it mean? Now, Brundtland, in his report in 1987 to the World Commission on Environment and Development, broadly defines it as the following. I hope I put it on top. So he defined it as meeting the needs of the present generation without compromising the ability of the future generations to meet their own needs. This is what Brundtland defined sustainability as. Now, I would like to share with you that the concept of sustainability, even though Brundtland defined it in 1987, nearly 45 years before or 40 years before, in India, people already started thinking about it. How do I say that? You can see this. Next slide. Kumarappa in 1945 itself, in his paper on economic of permanence in Sarva Seva Sangh Prakasham, Varanasi, India, actually started defining what is sustainable development, what is sustainable society. So according to Kumarappa in 1945, he said, a society which manages its economic growth without causing irreparable damage to the environment. And sustainable society satisfies the needs without jeopardizing the prospects of future generations. So that means the awareness of sustainability was much before even people started thinking at the international level, and that is the importance of Indian thinking, which we today do not want to give too much weightage, but India was always leading from the front. Now, sustainability itself has multiple dimensions. Now, you can look at this sustainability as a thing is actually supported on these three pillars, which are the powerful tool for defining, analyzing issues of sustainability. The three pillars are social, environmental, and economic. Let's look at it in greater detail now. Now, what is this? If you look at the things, when it comes to describing sustainability, we need to be concerned about three main areas of influence. They are the three interconnected spheres, which I will show you in the next slide. They are called as spheres of sustainability that describe the relationship between the three spheres. One representing environment, the other is economic, and the third is social. All these three things has to be addressed. Not merely technical issues or solving a technical problem is not good enough. A technical aspect of it is one small part of it. Unless environmental, economic, and social aspects are also considered, we cannot really achieve sustainability. These three spheres are a related set of concepts that, when taken together, can form a solid ground from which major decisions and actions can be made. Examples of such decisions include land use planning, surface water management, building design and construction, and even lawmaking. Now, let us try to understand in greater detail the three spheres which I discussed now. The three spheres, as I mentioned, environmental, economic, and social. Now, if you look at environmental, it has natural resource use, environmental management, pollution prevention. The economics are profit, cost savings, economic growth, research and development. Coming to social, it is education, community, standard of living, and equal opportunity, irrespective of caste, creed, color, whatever it is. Now, when you look at only environmental and social economic things, the intersection will tell you you have been able to achieve environmental and economic aspects of sustainability, which is energy efficiency, subsidies, incentives for natural use of resources. But if you look at only social and economic, what you will give, you see, is the fair trade, workers' right, business ethics. Similarly, if you look at only environmental and social, you'll only be looking at environmental justice, local and global natural resources stewardship. But if you really look at sustainability, the intersection of all these spheres is where you will achieve sustainability. And in this case, you can very clearly see where this is the area where you will see sustainability, where all these three spheres of environmental, social, and economic will intersect, and anything which falls within this is what we call as sustainability. Gibson also defined sustainability with an added one. His things were environment, energy, equity, and economy. And he said a condition in which natural systems and social systems survive and thrive together indefinitely is sustainability. You may thrive for a small period, that is not sustainability. It has to survive and thrive for indefinite amount of time. That's what Gibson defined sustainability as. Now, when we talk about all these things, we do very often talk about the greenhouse gases. The greenhouse gases are four of them. The significant amount is carbon dioxide, which is about 76% in our atmosphere. And the next largest is methane, which is 13%. Then you have nitrous oxide, which is 6%, and fluorocarbons, 5%. And these are broadly some things. Now, if you look at the damage index of these four GHGs, that is greenhouse gases, in terms of its damage index, in terms of with comparison to CO2 taken as one, even though CO2 is highest, what you will see here is methane is about 20 times more damage compared to carbon dioxide taken or normalized as one, whereas nitrous oxide is 200 times, whereas fluorocarbons, which are used in refrigerations, which are today significantly, after understanding we have reduced it, is about 15,000 times. So that is the kind of impact these four gases have on the planet. So the topic of today's faculty development program is sustainable construction materials. So it is concentrating on construction materials, then the practices and technologies. Keeping in mind, I am going to talk about one of the earthen materials, which is called a rammed earth for construction in civil engineering construction. Now, people say concrete, which is largely used in civil engineering construction, large amount of things. In the last 110 years, we are using Portland cement concrete. Earlier to that, the binder was lime, so it could be Surki or lime concrete. But Portland cement concrete, we say, is not sustainable. What are the reasons for it to be not sustainable in relation to the greenhouse gases just now we discussed? And not only that, other things also. The first is concrete industry consumes huge amount of virgin materials. Even in the production of Portland cement itself, we use large amount of virgin natural materials. And the other thing that we use in concrete industry is to have fine aggregate and coarse aggregate. Even though they are inert, they are also going to be, we use large amount of natural materials. We quarry, like for example, fine aggregate, we are using river sand. Now it is banned. Now you can see a lot of quarrying that is happening in order to get the coarse aggregate. And now, in the absence of fine aggregate from river sand, we are now crushing this rock and making it as what is called M sand, called manufactured sand, which is again utilizing the virgin natural resources itself. So the rate at which concrete is being consumed to meet the needs, the infrastructural needs of mankind is so large If you look at concrete, it is second to, after water, it is the second largest material that we use actually. Secondly, as I said, we also produce Portland cement, and the production of Portland cement gives out greenhouse gas emissions, and that is implicated for global warming and the resulting climate change. The other issue is the lack of durability of concrete structures, which adversely affects the resource productivity of the construction industry. For the following three reasons, we say concrete industry is not at all sustainable, and we need to address this issue. Let us look at some facts about carbon dioxide emission. Now, before industrial revolution, the Earth's atmosphere contained about 280 ppm parts per million of CO2. Once we started burning fuels for our transportation and energy, and in 1950, it had already reached 315 ppm. The CO2 level is now almost is much more than this. I just took the statistics. About a week back, it was around 424 ppm, and it is rising roughly at the rate of 2 ppm annually. Now, the Intergovernmental Panel on Climate Change has predicted what is going to happen, and by 2000, this IPCC said unless we make corrective actions and do not allow the CO2 to keep going at the rate of 2 ppm, it is going to be very, very harmful to the mankind and to the planet. And some suggestions were there. Decisive decisions were taken in 2008. And if those decisions are implemented, then the likelihood of arresting further increase and saving the planet has been known to all of us. Let us continue to see what happens. Now, some more facts about carbon dioxide emissions. There is no magic bullet to stop this global warming quickly. A number of reports have indicated that approximately about 450 ppm of CO2 is the threshold level. That means if you cross this threshold level of 450 ppm, it would have already caused irreversible damage to the planet. The window of opportunity, therefore, for mankind is very, very small, and we have to immediately take action to slow down the rate of further increase in CO2 levels, and eventually to bring it or keep its level below 450 ppm, so that there is no irreversible damage. And this is again taken from some of the studies by McKibben in the National Geography in October 2008. And the chart onto your right side very clearly shows if you take corrective actions, then you may be able to bring it down in the near future. But we need to take a lot of actions, not just one. Now let us go to some more facts about CO2. What is this CO2? In Earth's atmosphere, carbon dioxide is a trace gas that plays an integral part in the greenhouse effect, carbon cycle, photosynthesis, and oceanic carbon cycle. It is one of the several greenhouse gases in the atmosphere of Earth. The current global average concentration of carbon dioxide in atmosphere is 421 ppm. This is as on May 2022. This has further gone up. It is 424 ppm as of 2024 March. This is an increase of 50% since the start of Industrial Revolution, up from 280 ppm during 10,000 years prior to mid-18th century. The increase is due to human activity. Burning of fossil fuels is the main cause of these increased CO2 concentrations and also the main cause of climate change. Other large sources of CO2 from human activities include cement production, deforestation, and burning of biomass. The present atmospheric concentration of CO2 is the highest for 14 million years. Concentrations of CO2 in atmosphere were as high as 4,000 ppm during Cambrian period, about 500 million years ago, and as low as 180 ppm during Quaternary glaciation of the last 2 million years. These are some things about CO2. Now, as I mentioned to you, we are now roughly about 424 ppm, and these are all. You can see from March 8th to March 17th, the readings and what is the ppm. So you can see on March 16th, 17th, we are already at 424 ppm. So 450 is the threshold level. We are just away from that. Now looking at per capita CO2 equivalent emissions in 2000. This is again taken from a paper in Current Science in 2006. Now this will show you USA, it has the highest per capita for 23. And you can see all other countries, Germany, United Kingdom, Japan, and India is compared to US, it's just 1.5 tons per capita. But India, China, and other developing countries are actually consuming huge amount in order to meet their needs of infrastructure. Now let us look at the top 10 CO2 emitting nations as per European Union's joint research in 2022. If you look at this, as I already mentioned to you, since we are developing a lot of infrastructure, not only we, even China. If you look at this table, China is, if you, so much of material, million tons of carbon dioxide, it is 12,667 in 2022. United States way behind, 4,854. India is 2,000, almost 700. Russia, Japan, like this. These are the 10 top countries which are in the data of how much CO2 they are emitting. Now, coming back to per capita. Per capita, the top 10 countries with highest CO2 emissions. Again, European Union joint research. If you look at this, we are nowhere. You can see small countries like Paulova, Qatar, Kuwait, UAE, Bahrain, they are all very high, 59, 35. The table you can see very clearly. Now, in comparison to this, where are we? US stands 13th with the highest per capita. Russia, that is about 13.68, while Russia is in the 20th position with 11.64. Japan is in 26th with 8.39. China is in 28th position with 8.2. And India is in 110th position with a mere 1.74 tons per capita. Meanwhile, a number of other developing countries, they do occupy higher slots or top slots, largely because of regulation issues in terms of its energy, transportation policies, etc., etc. So let's come back to our civil engineering material, that is concrete itself. Portland cement production is highly energy intensive. The industry is consuming energy at an annual rate of 7 billion gigajoules of energy. The cement industry is also implicated in global warming. Portland cement clinker production is releasing nearly 1.5 billion tons of carbon dioxide, which is approximately about 7% of the global carbon emissions. Now, modern Portland cement concrete, because it cracks easily, it will have poor durability. Thus, the material efficiency, which is called resource productivity of concrete industry, is very low. Let us look at concrete and Portland cement. Global usage of concrete, as I already mentioned to you a little early, is second only to water. The demand for concrete is on the increase in order to meet the infrastructure developments, especially in developing countries like China and India. Current Portland cement production is insufficient to meet the increase in demand for concrete. Do we increase? No, that just because it is insufficient, is there that we can increase Portland cement production, or can we use alternative binders to meet the increasing demand for concrete? Is the big question in front of all of us. What are the issues with Portland cement? Portland cement production releases high amounts of CO2 to the atmosphere. We know that production of 1 ton of cement clinker, almost earlier it was giving 1 ton, but today with changes in the production technology, we are about 750 kgs of CO2 is released into atmosphere for every ton of cement clinker that we produce. Whatever is giving out is in two things. When calcium carbonate, that is lime, is heated at high temperatures, it actually gives out CO2. There is nothing anybody can do about it. And other energy, that is in order to energy that we use, that also consumes a lot of things and gives out CO2. So Portland cement production, whatever we may do, it will give out CO2. Now, Portland cement production is highly energy intensive after aluminum and steel. which is also the construction materials. Now, there are different strategies which are suggested in the literature to reduce the carbon dioxide. So, what are the things that have been looked at? One of them is carbon capture and storage. Okay, we cannot stop carbon dioxide emissions. No, we want to limit it in the atmosphere. Cement production we cannot stop because we have not still successfully in producing or coming out with a new binder. So we have to still survive. Therefore, Portland cement production will continue. Some carbon dioxide eventually, whatever be the efficiency of our production techniques, still it will give out. So one way is whatever it is coming out, you have strategies to reduce it by capturing that CO2, not releasing it to the atmosphere and storing it is one of the things that they have tried out. Awesome. Then second thing is, can we reduce the amount of Portland cement in our concrete? How is it possible? By using supplementary cementing materials like fly ash, GGBS, rice cash, and so many other things which are available so that the amount of clinker that we consume in concrete can be brought down. Then the third one is use of nanotechnology. I'll come to it a little later. And the fourth is look at alternative binders, which are the alkali activated binders. Now, these approaches which I discussed are not really feasible. What are the reasons? For example, carbon capture and storage. It is a very cost intensive process and it needs lot of storage. Economically very, very unattractive for cement industries. If it is so unattractive, nobody would like to use it. Nobody would like to use this process. Coming to the use of supplementary cementing materials, which are called SCMs, it compromises the concrete properties. What are they? Reduced early age strength when you use fly ash. It's a pozzolanic material. It takes a lot of time. It will gain its strength very slowly. But we are not, we want, the world is so fast. Reduced later age strength as well with limestone. When it comes to use of nanotechnology, high cost nanomaterials for commercial use, and there are issues with agglomeration of these nanoparticles. When we talk about nanotechnology, nanomaterials is much, much finer than cement itself. So to produce these materials at that size is not feasible from commercial point of view. And even if you produce, agglomeration is a big issue. And therefore, nanotechnology is also not a solution. Now, people have come out with an integrated approach in order to address the limitations discussed so far. For example, the figure on the flow chart, which is shown on the left-hand side, tells you about the whole process of production of Portland cement. Now, whenever the limestone, as I mentioned to you, is being heated, that is called a pre-calciner in the rotating kiln, that is where the carbon dioxide comes out. CaCO3, when it is taken to high temperatures, the CO2 comes out, and this CO2 needs to be captured within the cement industry itself. So very clearly, number one, it is CO2 produced in this process is captured and purified and stored, not even coming, it comes out. There is no need of use of large storage. Now, once you capture that, then use it in the cement industry, purify that, and pass it through a calcium solution. When it is done, you will get calcium carbonate. Now, grind it into nano-sized particle, intergrind it along with the clinker that is produced, and it becomes a part of it. And package it and market it as a binding material. And if required, you can also add the supplementary cementitious materials in the production stage itself. And this can end up in a sustainable, economic, durable cement. What are the merits about this integrated approach? The merits are captured CO2 is used within the cement industry, thus avoiding the need for storage. It offsets the limitations of supplementary cementitious materials, thus allowing for larger reduction of cement clinkers. Third one, avoids the issues of agglomeration in nanotechnology through dispersion process. Fourth one is generates potential economic revenue to cement industry, and therefore cement industry will accept this. Fifth one is it improves the performance of concrete, that is the durability, while reducing the carbon footprint of cement industries. This is the very latest paper which talk about an integrated approach so that you can address the CO2 emissions in a very efficient manner as discussed in this slide. Now let us look at the cement value chain itself. Here you see the picture. What is shown here is the production of cement itself. What you will see, the raw materials are extracted and you preheat the whole thing in the rotary kiln, very high temperature, almost 1100 degrees centigrade, and then you cool it. And here is the places where you can add supplementary cementitious materials. And here, when you are doing this, carbon dioxide comes out, and you are also using as a fuel so many other things which gives out carbon dioxide. And the finally the cement clinker is powdered and it is stored here and packed. Now this is Portland cement binder. Then you also use in concrete sand, that is fine aggregate, and gravel, and then water which is there, and some other other admixtures to improve the properties of concrete both in the fresh and hardened state. These are the additives or admixtures. And then you have your buildings, you have ready mixed concrete, on-site concrete, other things. After doing all those things, what really is going to happen is the life of the building, when it comes to an end for several reasons, we demolish it, and there are so much of it. Unless otherwise, don't have to use it as landfill. If you can use this, recycle that. Recycling the construction demolition waste, then use of will significantly reduce the use of virgin materials, natural materials. So this is the cement value chain or the concrete value chain, which is very clearly seen in this case. Now, how do we meet the increased demand for concrete? One of the ways is partially replace up to 60% use of important cement concrete by high volume fly ash, HVFA in concrete. You also develop alternative binders to make concrete, like for example, fly ash based or GGBS based geopolymer concretes. We will now come back to narrow things, which is the low carbon building materials is what they talk about. What are these low carbon building materials? Why it is low carbon? Efficient use of the available material resource. It is energy efficient. It is recyclable. It reduces GHG emissions and CO2 concentrations in the atmosphere. So if it satisfies many of these things, then only it is eligible, qualified to be called as a low carbon material. We will today's lecture or today's discussion will concentrate on one aspect of this where earth is used, and that is called as the rammed earth construction, both in the stabilized form and in the unstabilized form. Then what is this rammed earth? Rammed earth is a form of unbaked earth construction. When I say unbaked, there is no need of firing, which we do in fired clay bricks. Therefore, it helps in no deforestation happens. That is one of the issues which I said. So you are now not going to burn at all. And this rammed earth is a form of unbaked earth construction. What are the things? The processed soil is compacted layers to form a component of a building structure, which is termed as rammed earth. Farm work becomes essential in this rammed earth construction, with the exception of rammed earth for foundation. Except for foundations where you dig a trench, put your soil, process the soil, and fill it and keep ramming. So you can also think about rammed earth construction, in which case rammed earth for foundations, no farm work is required. For all other building elements, you require a farm work. A rigid farm work is mandatory. This type of construction technique finds application in the construction of walls, foundations, floors, and so on. Now let us look at history of rammed earth itself. Is it something new, innovative today we discovered? No. Rammed earth has been used for construction of walls for several centuries. You can see rammed earth in the Great Wall of China in the 3rd century itself. The Phoenician, Phoenician settlements in southern Europe in 7th century used rammed earth. Rammed earth buildings are found in Himalayan region of India and Tibet around 8th century. Old buildings in Middle East and Africa constructed thousands of years ago, they represent some of the historical rammed earth constructions. There are large number of modern, that is what we are doing, which is in some form stabilized or unstabilized rammed earth buildings, which have been built in the last 3 decades world over. I can show you pictures a little later. Now, what are the advantages of rammed earth? Rammed earth can provide aesthetically pleasing surface textures. A few slides later, you will see how pleasing the aesthetics is with colors by careful selection and preparation of materials. Very, very colorful things, good surface textures can be obtained. It reduces the carbon dioxide emissions. It is fire resistant. It offers flexibility in wall thickness. Strength requirements can be tailored by suitable mix design. Flexibility in plan forms. Walls can be built straight or curved in plan. Dense and bulky and hence has considerable thermal mass and offers scope for passive environmental performance. What are the different types of rammed earth? You have two types. One is unstabilized rammed earth, which do not use any organic additives. In the raw form, it is used and it is unfired. The other one is stabilized rammed earth, which uses inorganic additives. The issue with pure soil or unstabilized rammed construction is, as we all know, soil has various components: gravel, silt, clay, and so many other things. But clay has, there are three minerals in clay. One is kaolinite, illite, and montmorillonite. All of them have swell shrink behavior, and therefore there is going to be issues with unstabilized rammed earth, and they will end up in poor strength. Dry strength, it is very good. In wet strength, it is less than half. And among these three clay minerals, illite and kaolinite is probably better off. Montmorillonite is the worst. Even with stabilization, it's not easy to control this swell shrink behavior. So, in order to address this filtering behavior of clay mineral, we try to use inorganic additives like cement, lime, etc. And that is what is called as the stabilized rammed earth. The disadvantages of unstabilized rammed earth are lower strength and thicker walls because of the low strength, and also loss of strength on saturation. It is when it becomes wet. It is, you can't protect it when it is rains. Erosion due to soil impact, rain impact, then high maintenance cost and prone to termite infestation. Now let us look at these two, that is unstabilized and rammed earth, and make a critical comparison of these two. Now the column on the left side will tell you about unstabilized rammed earth, but some good things and also problematic things. It uses natural materials and therefore negligible environmental cost at the end of the life. That means when you don't want to pulverize it and you will get back, recyclability is there. Good moisture buffering properties. In fact, thermal things are very good here. Lower cost and scope for self-help construction is possible. Very low embodied carbon. Lower strength and hence thicker walls. Loss of strength and stiffness and moisture absorption is an issue. It is prone to erosion due to rain impact. It is prone to termite and insect infestation and damage, especially in tropics and subtropics. Now, in comparison to this, let us look at stabilized rammed earth. It has higher strength compared to unstabilized rammed earth, even in the saturated condition. Easy to achieve desired strength and scope for taller buildings. It is possible to build thinner walls, unlike unstabilized rammed earth. Use of inorganic stabilizers such as cement, lime, others is mandatory. Higher there, because of this, higher embodied carbon when compared to unstabilized rammed earth. It has better durability and good erosion resistance compared to unstabilized rammed earth. It is also free from termite and insect damage. So each one has its own advantages and disadvantages, and we have to be very carefully selecting this based upon the requirement and our needs. Now, coming to materials that are required for rammed earth construction, let us discuss that. Now, if you look at materials for rammed earth, the raw materials that are required, it is soil, sand, and gravel for unstabilized. There is no organic material. There is no cement binding material here. The soil, the clay itself will become a binder, but unfortunately, the clay in the dry state becomes very good binder. In the saturated state, it loses all its binding properties and therefore losses. There is a loss of strength. But for stabilized rammed earth, in addition to these three, soil, sand, and gravel, we use a stabilizer, which can be cement or lime in the stabilized rammed earth construction. Now, again, these raw materials, soil, sand, and gravel, the particle size distribution is very, very much important in order to achieve rammed earth construction. Now, when it comes to soil, the graph here very clearly shows the particle size distribution and the band within which the soil has to fall for good rammed earth construction. So as long as the soil that you are using for rammed earth construction, if you do a particle size distribution and see that it is within this band, then it will end up in good rammed earth construction. So roughly the sand and gravel are 45 to 80%, silt is 10 to 30%, and clay is between 12 to 15%. Now, again, let's come back to what are the kinds of soils that are available to us. There are four kinds. The first one, which is available, is the red loamy soil or the red earth, what you see very commonly in Bangalore and other southern parts of Karnataka. Uh, these are reddish to dark brown colored soils. They generally contain predominantly less expensive clay minerals, as I mentioned to you earlier, like illite or kaolinite, and the clay size fraction less than 2 microns ranges between 5 to 40%. The swelling and shrinkage associated with such soils is very small when compared to swelling and shrinkage of expansive soils like black cotton soil, which has a lot of montmorillonitic like clay mineral. The second is, as you go to the north of Karnataka, you will see black cotton soil. It is good for agriculture, particularly cotton, then groundnut and other products, agricultural things. But these soils contain considerable amount of expansive clean mineral, what I already mentioned to you, montmorillonite. Such soils are characterized by the presence of very hard clay lumps in dry condition. Now, the soil shrinks badly, that is volumetric shrinkage, something like 200 to 300% on drying, leading to wide cracks in the ground. These soils possess high liquid limit in excess of 50%, depending upon the quantity of clay fraction and the type of exchangeable ion associated with the clay mineral. It is difficult to stabilize black cotton soils even by using Portland cement or lime alone. The third one is the ash modified soils. This is a special kind of soil often found black cotton soils zones. This soil is called Halu Mannu in Kannada. It is also called as Gadki Mitti in Hindi. Such soil deposits are mined and the soil is used for construction of buildings for walls and roofs. These soils contain 2 to 3% of organic matter in addition to 5 to 6% of dissolved salts. They are known to be artificially made soils by mixing organic matter and wood ash and allowing it for very long durations for natural cyclic wetting and drying cycles. These soils exhibit very low swelling and shrinkage characteristics and are silty in nature. The Halumannu is well suited for stabilized compressed earth block production, either using lime or cement as the stabilizer. The ash modified soils show excellent reactivity with stabilizers like lime and cement when compared to natural soils like black cotton soil or red loamy soil. The last one is the lateritic soil, which are found in Kerala and coastal parts of uh, Karnataka. The term laterite was first introduced by Bouchnan in 1809. The laterite was described as ferruginous, vesicular, unstratified, and porous material with yellow ochres. Laterite can be cut into blocks. In fact, these regions, the soft material is cut into different shapes and allowed to for carbonation exposed to atmosphere. It takes away the carbon dioxide and it is made into masonry units. And that is why in Latin, the lateritic soil, later means brick. The laterite soils have low silica, very high alumina in hydroxide form comparable to the form in bauxite. The laterite occurs up to several meters depth, and you have so many things, but you also have sequoia oxides in this case. The sequoia oxides, you can see in the footnote in blue, what is it? Now let us come to the next step of construction of rammed earth. What are different steps? One is processing of the soil. Second is setting up of the farm work. Third is compacting the processed soil in these farm works and curing and later drying. These are the four major steps involved in construction of rammed earth for walls. Now, what is processing of soil? The steps involved in soil processing are breaking the lumps and screening, that is sieving them up to 5 mm size, mixing of this soil with sand and gravel in a dry state, and mixing this mixture with cement or lime if it is a stabilized rammed earth in the dry condition, and later adding water to this. How much of water has to be added? It is slightly wet of OMC, the optimum moisture content, what we generally do through in geotechnical tests. That is 5 to 10% wet of OMC is the amount of water that we need to add. And when we do that, the picture what you see in this slide, this is the final mix, which is about to be poured inside the mold and wrapped or compacted. So this is the kind of mix. Too much of water is very bad. It has to be slightly wet of OMC. OMC is optimum moisture content, 5 to 10%. Now, the quantity of water to be added depends upon the soil composition. Generally, about 10% water is sufficient to bring it to a consistency suitable for compaction. Too much water makes the soil sticky and poses problem during the compaction. Now, next step is the setting of the farm work. Farm work is, as I mentioned to you, it is a must in rammed earth construction. There are variety of farm works ranging from simple wooden traditional farm works to very sophisticated metal farm works. A rigid farm work is very much important. These slides show you this simple, small steel metal farm work that has been used by many of us. These are the people who are doing some things in IISc. Now you can see this is a mold, steel mold, very stiff mold, a lot of stiffeners, and a small portion is done and the mold is moved. And the same mold goes on getting shifted and rammed up. And all the vertical joints later will fill it and close these vertical joints. Now these are the simple wooden formwork, what you will see here in this slide. So this is set up and then the prepared soil mix with stabilizer or without stabilizer is put into this and rammed, manual ramming. Now these are much more sophisticated kind of metal farmers, which these are pictures in this case. The top left and right side are the ones in France what they use for unstabilized rammed earth construction, whereas the picture on the left bottom is the condition in within the country in India. Now, large walls when you want to build, then you also use large dimension formworks. But the problem is when you have such long lengths, there could be shrinkage cracks. You can see this more so if it is in the unstabilized form. So you can see some long formworks without joints. People don't require joints, but later there will be cracks. Then again, you have to treat those cracks. Otherwise, there will be these insects, ants, everything can create trouble within if you are it is a house or even if it is any other building for that matter. So these are all bigger metal formworks. The formwork cost goes up only when you have multiple kinds of construction, a large housing complex, building 500, 600 houses, then you may be affordable to use such very big metal formworks. The third thing is compaction of this processed soil, which is poured into the mold. The processed soil is poured into the farm, in the farm work, and then it is compacted in layers. You can't fill the entire thing and do it in one go. Normally, layer thicknesses vary between 100 mm to 150 mm, and that is when you ram, you will be able to get the proper density. Thicker layers, if you make it more than what we have suggested, it will lead to stratification and non-uniform density, which hurts the strength as well as durability. The degree of compaction measured by density has to be very, very nicely controlled. How do you do the density control? You can carry out. So this can be carried out by pouring a definite quantity, weighed quantity of the material into a mold and then compacting it. Now, for what volume, if you compact, it will reach. We will be able to achieve the required density. We know that. So therefore, you continue to ram until the desired volume is reached. Through this process, we will be able to achieve the required or aimed dry density of the rammed earth. It is preferable to leave the mold in place for 1 to 2 days. You cannot demold it. At least for 2 days, we have to leave it there before the mold is demolded and reused again for further construction. Now, the kind of rammers that we are using, you can see in the slide or the picture on the left-hand side, there's a manual rammer with a flat bed, and you should not be too heavy also because it's a manual thing. The person who laborer has to move it up and down and give an impact, and you can see in this mold the ramming being completed. Now you will see there is another special type of rammer which is a conical shape on the right side. This is actually after each layer is rammed to its required density, this conical one is used in order to make depressions so that there's an interconnectivity between subsequent layers so that there is no weakness along the rammed layers. So that is the purpose of having this special type of rammer in conical shape to make dents on the compacted layer. I'll show you how the dents look like. Now, these are also pneumatic rammers where labor is a problem, then you can use compressed air, and through this you will be able to have some kind of ramming which is done, which we will have much more efficiency. And this is what people use abroad. Even in this country, it's not a very big technology. You should have a compressed air, and you can do pneumatically as well when there is a labor issue. Now the finished rammed earth compacted layers, you can see each one of them. What you see here is in this panel, this small one, these are the two layers, right? First, this layer. Second, this is in one go, one mold. This is the mold. So one layer, two layers, and after this finished, after 2 days, the mold is moved left or right, and the next portion is done. And this is how the layers, you can see here also, you can see this is the layer. You can very clearly see that kind of where exactly the compaction was done, and layer by layer the construction is continuing. Now the last step is to cure. Now these are Portland cement if you're using as a stabilizer, or even unstabilized things, it have to allow it to dry. So curing and drying is the common word that is used. Unstabilized rammed earth walls do not require any curing, but they have to dry. Walls are allowed to dry before erection of roofs and floors. Cement and lime stabilized earth needs curing for the hydration. Then the surfaces of walls are covered with straw or gunny bags, and curing starts after 24 hours of casting. Water has to be sprayed on these exposed walls surfaces 3 to 4 times a day to keep it wet for a period of 28 days. Now, people have also used much advanced kind of a thing, which is called as pneumatically impacted stabilized earth, which is called PISC, P-I-S-C. This utilizes one side formwork, not on both sides, one side. And at high pressure, this mix, what we have produced with more water, is sprayed onto this mold layer by layer in the elevation, and you will be able to achieve, and then you have to finish. Later slides, you will see the process. Now, rammed earth method like PISC employs a mixture of earth and cement, but the mixture is compacted in two-sided forms using local materials with a minimal carbon footprint combined with steel reinforcement sometimes. We create beautiful structural walls. These walls provide thermal mass, stabilize interior temperatures, providing heat in winter and keeping the home cool in summer. The finished texture is smoother than PISC, and rammed earth walls have more of look and the grain of the ancient sedimentary stone. Once the walls are completed, the wooden formwork are used for roof sheathing and to conserve materials. This is one way in which you see it is sprayed. The material is sprayed, and the next slide tells you how it is being finished. Maybe a little later I can show you. Now let's come back to some examples of rammed earth construction, both in India as well as abroad. There are historical structures made out of earth. As I mentioned to you a little early, Great Wall of China, which was built in 13th century. This picture shows the rammed earth. And then you will also see the picture on the right side, the adobe brick walls at Ramesseum in Egypt, which is approximately 2,500 years ago. These are all again earth-based kind of constructions, historical structures. Now, this is the view of ancient Bam. The picture on the top shows you this is completely earth construction, something like 575 to 300 BC. Now, the picture on the left side bottom, where it is a entrance gate, this is the Argi Bam citadel in Iran, where you will see the beautiful natural things. And you will also see the picture on the left side, the stables, courtyard in the same Argi Bam complex. But unfortunately, all these earthen structures were damaged during Bam earthquake of 26 December 2003. Now you will see in the next slide, the picture on the left is a rammed earth building in Rhone Valley, France. These are all unstabilized rammed earth. Then you will see in the picture onto your right side, the traditional earth houses in Morocco. Now this slide gives you 3 pictures where you see tall structures with load-bearing adobe blocks in the top. This is in Yemen. Then the picture on the left side bottom is a 6-story unstabilized rammed earth building in Germany in a place called Wielberg. I'll tell you, because it's unstabilized, the wall thickness was at the ground floor was 750 mm. Then you see on the picture to the right side a 4-story rammed earth house in Bhutan. Wall thicknesses at the bottom was 1.35 meters, built in 18th century, but the picture itself was taken in 2009. So we are also having earth constructions in our own state, Chitradurga Fort. You can see the ruins of cob walls in Chitradurga Fort Palace. These are all things which built in 16th and 17th century, and this picture was taken in 2018. You can also see on the picture to your right side special shaped adobe blocks which are handmade without any use of mold during by Nayaka rulers in the Nayaka rulers palace, Chitradurga Fort again. This picture was taken again in 2018. The structure itself is 17th century AD. Now you will see other kind of things in this slide. On the left side, Royal Rammed Earth in Granada, Spain. On the right side, you will see multi-family apartment building using rammed earth. This is again in Germany. Now this is another beautiful looking, natural looking kind of structure, which is the Swiss Ornithological Institute. It was built 2013-14. It's a prefabricated unstabilized rammed earth panels for use to construct this building. Now this is in India itself, 3-storied load-bearing cement stabilized earth dormitory building built in 2019. The first publication in India, you can see Indian Concrete Journal, April 15th, 1950, use of soil cement in houses construction in Punjab. Some details are there. This is extracted from this journal paper. Then again, in 1841 in Wielberg, in Germany, we had this kind of G+2-story building with rammed earth. And you will also see the same view of the building on the other gable wall side. Now, I had shown you earlier also in Germany, a 6-story load-bearing unstabilized rammed earth, and the wall thickness from ground to the top, 750 mm in step sized up to 300 mm as you go on top. 750 is required because it's unstabilized rammed earth for wall construction. Now, this slide tells you in the top left, you will see a school building in Bangalore, which we ourselves did at Indian Institute of Science. Then you will see on the right side top, there's the lecture hall complex of the Department of Civil Engineering and Structural Engineering Group, which we ourselves used and got a rammed earth. We adopted rammed earth for our lecture hall. And you will see on the picture to the bottom, I had mentioned to you about different colors that you can get on the surface, beautiful looking things. And this is one example in Germany. Now you also have in UK, these are some pictures of buildings of rammed earth in UK. You can see this pisse kind of thing where you are spraying and then you have to finish it, and you see the beautiful rammed earth construction. But there is a lot of wastage of material. This is the picture which I had already shown you. Now coming to the literature, we have a book, Rammed Earth, Design and Construction Guidelines, authored by Peter Walker from Bath University and other 4 co-authors. It is published in 2005. There are numerous papers which addresses the engineering properties and other issues of rammed earth, which is available in journals. This is a rammed earth Basgo Fort in Ladakh in India. You can see this was also a rammed earth construction using earth. When I went to, we had an international project with France, and in that exchange program, we have faculty from India who used to go there. And one of my visits, this is what I have taken a picture, unstabilized rammed earth construction in France, in a place in Lyon. You can see the close up here. What they also add is bigger sized pebbles also. This will help in controlling the shrinkage because of too much of fines in rammed earth. So usage of any of these kind of big sized particles is also a good thing. This is a close up of whatever I showed you the other level. You can see the pebbles very clearly in this slide, in this picture. This is again another building in Lyon, on the outskirts of Lyon, where rammed earth unstabilized form has been used. This is in Australia. When we went, there was a specialized conference on rammed earth construction thing itself in Perth, in Western Australia. And in that visit, we also found the practices of rammed earth construction in Australia. This is a picture which I have myself have taken. This is again in Australia. They build apartment complex, unstabilized rammed earth. Now let us come to the other aspects, which is testing. Now, how do you do an engineer in order to evaluate the engineering properties? And the first thing that we have to look at is the compressive strength and the stress strain characteristics of rammed earth. What kind of specimens and what is the testing that we have followed at Indian Institute of Science? Now, as I mentioned to you, the soil that we use should have clay content maximum 15% or 20%. And for that, we try to have a particle size distribution also. If the soil has more clay, then what we do is to add silt or sand to bring down the clay content. And such soils are what are called as reconstituted soils. So in this picture, we are looking at soils S1, S2, S3, S4, and S5, and river sand, which was used to dilute or to get the reconstituted soils, and the particle size distribution of all these material, four kinds of soils reconstituted, and also the river sand. Now, these S1 to S5, you can see what was it. All of them had one amount of soil, that is quantity of soil. The first soil, S1, did not have any sand, which ended up. Hello? Shall I continue? Hello?
Yes, sir. Please continue.
Yeah. So S1 is, there is no, it is not reconstituted. The soil had about 0% sand, 50.3% what was there earlier itself in that. We didn't add anything extra, 18.1% silt and 31.6% clay. Then, in order to bring down the clay of 31.6 to lower levels, S2 we added over and above the sand which was there in the silt and sand, 0.5%, so that you see it is brought down to 21% clay. Like this, we brought it down. S5 is 9% clay only, but we added 2.5 sand to the soil. And that is how we ended up in 9%, 12%, and 15.8%. That is S3, S4, S5, which are called reconstituted soils for rammed earth construction. Now, first step we do is to cast cylinders. The cylinders are the picture above. You will see the cylindrical mold, and we fill this with this mix, whatever it is, and manually compact it. That is, consolidate the whole thing, and you will see these kind of cylinders which are 38 mm diameter and 72 mm height. These cylinders are produced after curing. This is what happens. We subject them to compressive tests to get the unconfined compressive strength. Whereas we also use CSRE prisms, which are 150 by 150 in cross section and 300 mm in height, so that your height to least lateral dimension is 2 in this case, similar to the cylinders, which are there. 72 divided by 38 is 2. So height to least lateral dimension we maintain at 2 to arrive at the compressive strength. Now, that is also not good enough. A big wall, a small thing, size effects will be there. Therefore, we go in for what are called the wallets as specimens for estimating or getting the cement, that is compressive strength of rammed earth, whether it is stabilized or unstabilized. So these are called as wallets. They are bigger in size. Now, here you will see the testing of a prism, 150 by 150 by 300 mm height. We are measuring applying the load in the uniaxial direction, and that equipment that what we use to measure the longitudinal strains, or the strains in the direction at which the load is applied. And you can see the wallet also in the picture on the right side in a test bed. And we also, what you see, the aluminum things that are held, that is where we put digital dial gauges in order to measure the axial strains or the gauge length of 200 mm. Now, coming to the optimum moisture content, now we say we are stabilizing it, and we looked at four soils, S1, S2, S3, S5. 0-minute lag means the moment we add water, immediately we try to get the specimens and the optimum moisture content at different time. So what this figure is showing you is, by the addition of cement, anywhere from 5 to 12%, the optimum moisture content is not getting altered. That's the thing. Whereas it all depends upon the soil type. For example, the soil with S, which is designated S1, requires higher amount of uh, for the same cement content, higher amount of water for OMC. This is again the maximum dry density, the relationship between maximum dry density and cement content. Again, for the four kinds of soils that we have discussed, and you will see as the cement content changes, what is it that is happening for the different soils at different maximum density. This is again optimum moisture content and how it varies with the clay content in the soil from small quantity to as high as 31%. So with different cement percentages as a stabilizer. You also have 0% means unstabilized rammed earth, and that is the least what you can see here. This is again trying to show you the maximum dry density versus clay content. What is happening to this for different cement contents, and five, that is 0, 5, 8, and 12%. So as the clay content increases, the density that is achievable keeps reducing. Now, this is a graph which talks about a combination of the two, that is maximum density on the y-axis on the left side, and the y-axis on the right side is OMC. Trying to combine these two things, how after time lag, that means after while we add water and you just leave it, don't immediately do anything. For example, the picture what you see, fresh mix, that is immediately, that is how the mix looks like. Then after 2 hours, you have added a stabilizer, water is added, therefore it becomes a lot of lumps will be created. And the slide with 4 hours, you can see more of lumps, and after 10 hours. Why are we are trying to do this? That means you can have a dry mix, don't add water. If you add water within reasonable amount of time, you will have to put it into the mold and ram it. Otherwise, it will lose its strength because of the hydration that partial hydration that would have happened. That is the purpose of this particular test that we did. That is, if you don't do it, what happens? You can see this next slide. The compressive strength, when you talk is wet compressive strength, immediately after mixing the soil, if you ram, you get 3.3 megapascal. Let us say after 10 hours, you mix the materials, put water also, don't ram it. Don't put it in the mold and ram. Then the resulting specimen, if you ram it later after 10 hours, you are going to achieve very small wet compressive strength, 3.3 megapascal to 1.65, almost it drops by 50%. So the importance of you ramming the material immediately after adding water is shown in this graph. This is coming to dry density and water absorption. After the specimen is cast, now you can immerse it in water and found out how much water it has absorbed. If the density is higher, it absorbs less water. When the density is extremely low, it absorbs large amount of water and therefore it loses strength. Therefore, how the density has a role in the saturation levels or water absorption ability. So higher density achievement is very important so that it absorbs less water or less moisture from the atmosphere. This is compressive strength with moisture at the time of testing. Let us say we simply dry the specimen means in the ambient conditions. So for all the 5 kinds of soils with 5% cement, we try to see how the moisture in the specimen at the time of testing is affecting the compressive strength. You can see the moisture in the specimen significantly drops the strength. This is again the similar kind of relationship where you have 8% cement. The previous one was 5% cement stabilizer. This is for 8% cement stabilizer. And density that we achieved here is 1800. In the previous one also, the density, dry density, we achieved full 1800. Now, this is a comparison for 8% and 5% for the two soils, S5 and S2. That is compressive strength relationship with moisture content at time of testing. This is how the clay content in the soil impacts the compressive strength. And I mentioned to you the optimum that we have found is 15% or 16% clay. That is for both 5% and cement, 5% cement and 18%, 8% cement. We found that the range is somewhere between 15 to 18, 19%. Clay content will give you the highest strength and also durability. Now, this is the table which gives you the numbers for S1 to S5 soil, the strength, what was there, and at the time of the 10th, what was the moisture content. And we also tried to give a relationship between the moisture content and its dry strength. So that is a predicted strength, and for both 5% and 8% cement in the Ramdar specimen, which was a valid. Now, the density versus compressive strength, you can see when the density is high, you get higher compressive strength. This is very natural even in concrete. And for different cement contents, both in dry and wet condition, how the density affects the compressive strength is depicted in this graph or relationship. This is again compressive strength, both dry and wet condition for prism, whereas the previous one also was there. And you can see this is again dry wet. But here what you see is density. In two specimens, it was 1600, 1800 density and 2000 kg per meter cube density. The moment you have higher density, lesser the water absorption, higher it will be dry as well as the wet strength. This is again saturated moisture content. That is, if you take the specimen and put it in water for 24 or 48 hours, it does not absorb entire thing. It reaches certain levels and gets saturated. Now, when the density is lower, it will have higher water content for saturation. And when the density is higher, the saturation water will be much lower. This is the stress strain characteristics. As I told you, the elastic properties, both modulus of elasticity and the Poisson's ratio. Here we have measured both the strain in the in the direction of load and in the orthogonal direction, which is called lateral strain. And for different kinds of things, for example, density 1.7, 1.8 gram per cc, cement 7 and 10%, and the testing conditions both saturated and dry condition. Saturated depends upon how much. It will be something like 15 to 20% water will be there, which is called wet strength. Now, after having done this test, we have the numbers now in this slide. For 7% cement, you see the initial tangent modulus was 2750 megapascal. In the wet condition, it is this. Dry condition is 3800. This is wet means saturated. Completely immerse the specimen in water for 2 days so that there is no further increase in the water that is absorbed. Then Poisson's ratio was around 0.1 and in dry condition 0.15 almost. Strain at failure and compressive strengths for both the cement contents. And the typical failure of this cylinder is a shear failure, what you can very clearly see in both dry and wet condition of the specimen at the time of test. This is again stress strain characteristics. For different cement contents, that is 5, 8 and 12%, and also for different dry densities, 1600 kg per meter cube, 1800 kg per meter cube, and 2000 kg per meter cube. What is the initial tangent modulus in the dry and the wet state, and the value of strain at peak stress for these three cement contents and for the three densities for dry and saturated conditions. These are the numbers. All these things were generated through tests in the IISc Department of Civil Engineering. And again, this was a repeat, I think. So why I have put this slide is the picture on your right side. This is actually, we know that the moisture which is there will not completely come out in the ambient conditions. Therefore, we try to put a specimen within so that from bottom, we try to heat at a maximum of 500 degrees centigrade, and hot air will be made to push through so that some amount of moisture will come out. These are highly controlled experiments to understand the amount of moisture in the specimen at the time of test and its relation to the engineering properties like compressive strength and modulus of elasticity. So when you do this process, we cannot 100% remove all the moisture. We can achieve moisture at around 2% or less than 2% is possible. But you will have to have such an arrangement with lot of heaters here, and the hot air will pass through the specimen and removes all the moisture, but not 100%. It will not be possible. So we also try to test valids of different heights to understand the influence of the slenderness ratio on the compressive strength of rammed earth walls. So the first specimen is 400 mm in height, the second is 600 mm in height, and the third is 900 mm in height. All of them here you can see 10% cement content, 1800 kg per meter cube is the density. And somewhere in 2014, we were able to cast the specimen and do the test. So this will clearly, the table below will tell you the strengths. And all of them were 55 mm thick. The length was 600 mm, whereas the height was varied from 400 to 900 mm. And the height to thickness ratio as a result of this will vary from 2.6 to 5.8, whereas in the case of cylinder it is 2. Two cement contents, both 7% and 10%. Each of these, you can see two different densities. Each, to satisfy all the parameters, we have to test 12 plus 12 plus 12. You can see how many number of specimens has been cast and tested. And the statistical values are what are reflected. Now, what you see in this slide is this is an international project between India and Australia. It is Indo-French kind of a project. So this is the setup that we have made for full-scale walls. In this test setup, I can test a wall of 3-meter height. So this has a 200-ton or 2000 kilonewton vertical actuator, servo hydraulic, and a 500 or 50-ton actuator in the horizontal direction. And we have tested 3-meter tall walls, which are about 1.1 meter in width and different thicknesses in this beam. This cross beam, which is used to apply load, can be moved up and down depending on the height of the specimen that we are testing. This facility is in the structures laboratory at Indian Institute of Science, Bangalore. And you can see this one, the testing of a wallet. And you can see several layers here. 1, 2, 3, 4, 5, 6, 7, 8, 9 layers are there. Now, I don't know if this video works. If it works, it is good. This is a test in progress. Generally, when I share, the videos don't work. I really don't know why. Okay, let's not worry. It is not working. Okay, let us look at the final failure itself. This is how the specimen fails in shear. You can see this is how it cracks at the ultimate things. This is the 200-ton load cell, and this is the 200-ton actuator actually. Okay, close up of this failure, you can see the shear failure. And here also you can see through the thickness how it has broken, the shear failure. Similar thing happens in the cylinders also, shear failure. Now, what is this? These are the specimen test results for 3 different heights. The height to T, that is aspect ratio, varied from almost 2.6 to 5.8. And moisture content at the time of test is also reported here. What we do is, after the test, we take lumps of this material in different places, put it in a small steel box and put it in oven. We don't take the temperature beyond 50 degrees centigrade and try to estimate what was the moisture content at the time of the testing. And we also try to, for this moisture content, because we have to make a comparison, no, we can't change. So we have to normalize this. So we have adopted a correction factor for moisture content change, and this is the corrected one. Now, this is this for the different specimens of different heights. What you will see here is there is no big difference in the compressive strength, 4.54 to 4.61. That means up to an aspect ratio between 2 to 5.8, the aspect ratio has no influence on the compressive strength. That's what it is. That's what is depicted graphically here. From 2 to almost 6, the curves are flat. For both cement contents, dry density 1.7 and 1.8 grams per centimeter cube. So up to this slenderness ratio, there is no change in the compressive strength. The correction factor, you can see this. The correction factors indicated are also this, and our test also showed the numbers which are very close to 1. No, we didn't leave it like this. We further went for higher height walls, that is 1500 mm, that is 1.5 meter, 2.1 and 3 meter high walls. In this case, we were able to achieve a slenderness ratio of 10, 15 and 20. And we also looked at eccentricity in the load. That is 0% means concentrically it is loaded. 1/12 of thickness, 1 eccentricity, 1/6 of thickness, and 1/3 of thickness of the wall are the eccentricities. And we looked at how the eccentricity is going to impact under high H/T ratio, the CSRE wall strengths. Okay, this is actually it has already completed. At that point of time, it was under progress. We have completed all the things. So this is the mold for very tall ones, tall rammed earth walls, 1.52. So we go on adding these pieces to increase the height to achieve higher height walls. You can see the process, the ramming is going on. So the bottom, the one side, the entire thing will be there. Then we only add the first piece so that you will ram until it is rammed until this level. Then add the second piece, then ram it, and like this we can go. Here you can see the conical dents, which I was talking to you a little early. This special kind of thing, it makes after a layer is rammed, we make such indents for interconnectivity between two successive layers of ramming. And this will give, this is like shear connectors. We also, in later you will see, we also applied cements and cement slurry in order to enhance the bond. So this is again, the video will not working. How we have cast elsewhere and what is the arrangement that we have to do, design the whole system to be transported to the test bed of the specimen. It's not easy, very heavy and very slender ones with unevenness in the ground in the laboratory we will have to bring. So we have taken special care to transport these specimens from the casting yard to the test bed. So you can see this is the kind of tall specimen. You can see the tall specimen with the steel plate. This has to be moved to the test bed. You can see the 3-meter high walls in the casting yard. Even there, we'll have to give such supports, otherwise it is going to be risky. Here, supports are removed because we wanted to move this to test. This is the curing in progress, wet burlap. Now, this is for drying to remove the excess moisture. Because when we cure, a lot of water is there. Before testing, we try to have electric stoves below. We have designed all these things. We also have a thermostat here. We ensure that the temperature does not go beyond 50 degrees centigrade. Hot air moves up and escapes out. In the process, it also removes the moisture from the specimen, but it's not 100%. It's around 1.5 to 2% will always be inside itself. Now, for eccentric loading, the kind of arrangement that we made with the plumb bob, and this will tell us how much eccentricity we are applying the load. So this is again another video, unfortunately, how we moved the specimen from the casting yard into the test bed. This is not working, unfortunately. Now the specimen is in the test bed and we have tested. Again, this is a video which is not working, but you can see the failure patterns. When it happens, whenever you have H/D ratio very large, the failure is not by material failure, but by slenderness effects, which is the bending will take place. And that you can very clearly see on the opposite faces in the next specimen. This is the compression phase, crushing that took place, and this was a tensile phase. So it simply opened up along the compacted layer. So this is what happens when the slenderness ratio increases. Now, the effect of slenderness ratio and concentricity and eccentricity, you can see this compressive strength is dropping when the eccentricity is increased from 0 to 0.15 or something like that for a H/T ratio of 10. So we further went to understand the shear behavior, which is the in-plane shear behavior, that is sliding as well as diagonal compression test. So if you have a rammed earth wall like this, always you have gravity load to withstand, which is compression. But in the event of lateral loads like earthquake or wind, there is a lateral load which is going to pay. Now, if there is small axial stress, then one of the possible weights of move along the rammed earth layers, it can slide. This is called a sliding shear failure. When there is a significant compressive stress, let us say this is a wall of a 3-story building, 4-story building, then the ground story will receive all the loads from the top, and therefore the compressive stress will be high. In such an event, in the when a lateral load is acting, you will not get sliding, but on the other hand, you will get a diagonal tension shear failure. So in order to understand both these shear bonds, we try to test specimens, both triplet shear test as well as a panel under diagonal compression as suggested by ASTM. So this is the triplet shear specimen. Now you will very clearly see this is the layer, compacting layer 1, then compacting layer 2, but actually we rotate it while the time of preparing the specimen or casting, and at the time of testing we rotate it by 90 degrees and we support the end things here. What you see is supported, and we also give a normal compression, and we only push through a servo hydraulic actuator system, MTS, the middle one. Now, this pre-compression is given different amounts for different specimens in order to get the Mohr Coulomb factors, that is C and phi, which is related to the shear strength, that is the interface shear. And we also measure the slip of the middle one with an LVDT as the load is applied. Once this interland, that is, there is a failure here, this middle block will slide and there will be deformation. So this is the casting, that is wooden molds for preparing these triplet specimens. And here you can see the depressions that are made with conical one. And here you will see we tried different bond enhancing mechanisms. One with these conical depressions, second with cement slurry pasted or brushed before the second layer is rammed. And we also had 3 methods which we will tell you, both depressions and cement slurry. This slide will clearly tell you, see, before the next layer is rammed, we have depressions and a cement slurry is applied, which will enhance, see, with a brush like this. You can apply cement slurry. Take cement, add water into a thick paste and apply it. This is the specimens for triplet after curing. So these are the layers. So you support here and push this. This is the test setup for triplet shear test. So the axial stress is applied through these jacks, here one and the other one. So there is a normal stress, and these two are supported, the end ones, and the middle one is pressed right through a MTS testing machine, and you can see the LVDT here measuring the deflection of the middle one if it is sliding. So this is the test setup. What did we do? We tried to get for different normal stress, that is when the normal stress is 0.3 compression, what happened to this load displacement. That is what I am trying to say is, in this case, what is the load and what was this displacement? That's what we plotted for both dry and wet condition. For 3 different, only dense, slurry only, dense with slurry. And this is the response, the load versus the triplet shear test specimen. This is for wet condition, this is for the dry condition. The same specimens were in the dry, that means about 2% moisture, whereas in wet means saturated condition, roughly 18 to 20% moisture will be there, water. And in this case, you will see different enhancement in bond strength has no impact in the wet, whereas in the dry condition, there is a slight difference, and also ductility is much more in one of the things. This is dense only is this, whereas slurry and slurry with dents are here. They behave much more ductile fashion with slightly higher compressive strength also. This is the C5 parameters. All the pre-compressions you can plot, that is whatever is the pre-compression values here, and the shear stress what we can measure or through experiments. And you will see in the dry condition, this case, this is actually the linear kind of a thing. So what is this rectangles? It is slurry only, dry, only slurry. Whereas here it's only dense. This is only in case of dense and slurry. So this is a C5 parameter. The intercept will give you the C, and the slope of this will give you the phi. In the wet condition, there is no big difference at all. Any enhancement, nothing will happen. And almost all of them have the same C and same phi. So these are the failure patterns of the triplet shear specimens. You can see the end ones, and this is the compacted layer, and here material failure happening. Some more pictures, how they have behaved. Now we went in for the ASTM tension compression test specimens. These are bigger panels. These are the mold for preparing them. And we apply diagonal load. These are the specimens ready for testing. And we apply a diagonal load. You can see the test setup. This is the ASTM loading shoe. There is a specification. We can get it fabricated. And along the diagonal, we put the specimen in a MTS compression machine. That is the servohydraulic testing machine. And we have to measure the deformations of these two diagonals. That is this diagonal and this diagonal. This is done over a gauge length of 600 mm. And this is for rammed earth. You can see using these two longitudinal, that is along the two diagonals, the deformation and the load, you will be able to compute the shear stress and the shear strain gamma, which I'll show you a little later. Here you can see, if in knowing the load and the cross-sectional area, you can always compute shear stress. From the measured strains, the horizontal and vertical diagonals, you can get gamma. And once you know, you can get the relationship and the modulus, shear modulus also, you can estimate. So here you will see the equipment here for measuring the horizontal diagonal strain as the load is in progress. And when the results we got in dry state, the shear stress versus shear strain, you can see in this case lot of in-plane loading, there is a ductility, it yields, and then without much loss of strength, there's the ability to deform. That is, shear strain is so high from this case to this case. This is exactly the ductility that you are able to achieve. This is in the wet case for different bond enhancement techniques. Still, you are able to get from here to here the deformation without much loss in strength. These are, say, failure patterns of the test specimens. You can see in the wet condition, it has broken along the diagonal, the crack has come and broken. You can see the crack here, crack here. This is the failure pattern of CSRE diagonal tension specimens. So what did we get? The secant shear modulus corresponding to 50% of peak shear strength. That means you are trying to compute shear modulus, not at full, only at 50% of DTSA. That is two kinds of specimens. They have found 3100 to 3850 megapascals. That is the G. The secant modulus, shear modulus corresponding to 50% peak shear strength of specimens. These two in wet condition. 3100 became 2700, 3850 became, continued to remain 3850 in the wet cases also for this particular specimen. Now, this is a video which unfortunately I'm unable to play. You can see a close-up of the test in progress. This is a wet condition. Now, we also try to look at the flexure bond strength. That is out of plane loading. Till now, we looked at in plane lateral loading, but you can also receive out of plane lateral loading. And for that, we need the flexural strength, or what is called the modulus of rupture, and two directions. Flexural stress normal to the bed joints or the rammed layers and perpendicular to the rammed layers. You will see in the case of perpendicular to rammed layers, this is the specimen. Now you will see the parallel and perpendicular. The strengths are very much. Whenever you have the normal stress perpendicular, it is only 0.5 megapascal, but in other direction you see 1.2. Therefore, easily showing that there is orthotropic behavior both in terms of strength and elastic properties. Now, this is the free vibration damping. Whenever the building is there and subjected to earthquakes, then in order to understand the behavior, you need damping. So what we did is we made two kinds of specimens. The flexural stress is normal to layers and parallel to the rammed layers, trying to see if there is any difference in the natural frequency similar to the flexural strength or modulus of rupture. In order to do that, we fixed these specimens and had an accelerometer, free vibration test we did. And from that, we were able to use logarithmic decrement for the specimen, as well as we also did a rammed earth building model. This is the response of the building model. This is of the specimen, whatever I showed in the previous slide. And we were able to get the damping from these two cases from logarithmic decrement, and we found damping to be 2.4% in both directions. Flexural stress parallel to rammed layers and perpendicular, there is no change at all. And this result, which we did, we tried to compare with the literature. There's a Bui et al. 2011. This is the paper. They also reported a damping of 2.5 to 4%, which was essentially for the unstabilized rammed earth. This is the logarithmic decrement method that we adopted. Now, when we talk about the building behavior, when it is made out of rammed earth or stabilized or unstabilized, we have to understand its behavior under base shaking, that is, in the event of an earthquake. Now, what are the equipments that are apparatus to imitate earthquakes and the historical development of these base shaking apparatus? The earliest is in 1890. So you can make a platform, you can make your specimen, and you connect it to this wheel and manually rotate it. The specimen will move to and fro in this direction. This was the first attempt of trying to produce an equipment to give base shaking to the specimen. This is the specimen. Now, the same thing after electricity was generated, instead of manual, they put an electric motor and tried to do it. This is 1906 at Stanford University. This is a piece, good kind of equipment which was developed in IIT Roorkee by Keatley in 1977 called the shock table facility. Now you have the table here with all the specimens to be tested, a building here and a sloping ground here. So this is again a wagon with full of load like this picture, and you allow it to come down, it comes and hits this table, and this will make to and fro motion. Similarly, in the other direction, opposite direction, and this is how they tried to understand the seismic behavior of the buildings. This is a facility which is called shock table at IIT Roorkee, railway wagon type. But the land required was so large. So what in IAC we did is we retained this, but to give this impacts, we used a pendulum kind of a thing, which you will see in the next slide. So the schematic is the table is here. You have a pendulum with 600 kg mass. You can lift back and leave it, and it comes and hits the table, and the table moves to and fro. And on this, you build your any structure to be understood. Its behavior has to be understood. So what are the different parts of this equipment is given here, which is a shock table at IISc. We also try to characterize the base motion with reference to the same parameters that are used to characterize earthquake ground motion, like amplitude, frequency, content, and duration parameters. And these are the few things, the shock table in IISc, then the earthquake parameters for PGA, PGV, SG, then Hosner intensity energy, and Arias intensity AI. These are again for the corner frequency content issue for that. And the shock table was giving very small strong motion duration, and therefore we had to modify this by adding a spring here. Earlier it was a gap, so we added a spring here and to increase the number of to and fro motions. That you will see very clearly the shock table which is modified with springs, and this is the pendulum. 600 kg mass is here and 1.8 meters length of this, and there is a pivot here, and you can swing it back and hit it, and therefore we will be able to give to and fro motion to table and therefore to the test specimen. Now, many other things we were trying to do. What we try to do is when it hits the table, you change the material to which it hits. In order to change the cap, one is wood only, plywood. Other is the plywood with rubber in between, or other is steel plate only, or steel plate with rubber. What you see, steel plate, rubber, and steel plate, that you can replace it here, and you get different kinds of forces in order to get different parameters of earthquake ground motion. We did also build a building and looked at the behavior on this shock table. And this was a rammed earth building. These are the typical plan dimensions. Then it also shows the window openings and door openings in this building. It is a scaled building model, which was 1.8 meters by 3.1 meters and 1.5 meters tall. You can see the building model on the shock table. This is the first version of the shock table without spring on the back side. There's a gap and a rebound facility. And we also measured, these are the accelerometers to measure the response. You can see this is the shear wall which receives in plane lateral load, whereas this wall and this wall will receive out of plane lateral load when this table is moves like this. And these are the accelerometers positions on cross wall 1 and cross wall. That is, this is cross wall 1, this shear wall 1. The building itself, we later did numerical analysis. So what did this have? The previous slide, what I am showing you here is there was no lintel band at all. It's a non-engineered building, only cut lintel on doors and window openings, no roof band, no earthquake resistant feature at all. So this was an unengineered building which we thought we would understand first, and later did numerical tests. Doing all buildings experimentally is costly, time consuming. So we tried to do one model, then create an analytical model, a numerical model, calibrate it, and further do only numerical experiments. So the parameters for the first model without roof, model with rigid roof, with all the features, earthquake resistant features like RC lintel band, and you also had the things which were like this. And we looked at the numerical things, finite element model, look at the modal mode shapes, different mode shapes for different building models, which were earlier described BM1 to BM4, and the values through FEM what we got, the frequencies. This is the kind of table motion that we were able to get. On the table also we mounted an accelerometer, and when it is impacted, what was the acceleration of the moving table, base excitation. And we compared that with the response spectrum for zone 5 as per IS 1893. And let us look at the failure patterns of this building model. What happened? You see from the lintel level two vertical cracks here, horizontal crack here, and also the in-plane shear wall had a diagonal crack from sill to the plinth level, like this, step kind. So this is the joint actually, this is the rammed there joint, and mold also we had to move from one to other, and that is how it moves like this, like a step. Again, few more pictures showing the failure, corner failure. What you see here is the two orthogonal walls at the time of interest, wherever they meet, this is called the corner failure. The box action is lost, and each of the walls, once it cracks, will act independently, and therefore they are more vulnerable. This is the failure. This cross wall fell down. Can you see this? Because of this flexural crack, very low flexural strength, and it collapses. This is a chunk of masonry which was here, or the rammed earth which fell down as a rigid body by overturning. These are some numerical experiments on using finite element with base motion. I will not get into it. This also, unfortunately, the test I wanted to show you in the video, I am unable to show you. Now, we further went to assess the fracture properties of CSRE. So we used different things. These are the specimens where you have notch, and we tried to use the 3-point bend test for geometrically similar notch specimens. Their damage already initiated. We tried to look at what happens here to estimate the fracture properties. So the parameters of the beam, specimen dimensions, and the notch depth, different notch depths that we do for understanding the fracture properties, which later can be used in analytical models. These are the dimensions of the specimen. These are typical tests under progress. We use DIC technique to get the deformation informations, and the damage which is inside, which is not visible, we use what is called as the acoustic emission sensors 1, 2, and 3. So they will be able to, through acoustic signals which it will capture, we'll be able to know when the damage actually started inside and reach the surface. So this is how we do the test. Some you can see the failure has extended, the crack has extended, and this is the DIC pattern that we recognized, that we use. So the load versus load point displacement response for the fracture specimens for different things. This is load versus CMOD, crack mouth opening displacement, and based on all these results, we will be able to get the properties. I'll just show you here the fracture toughness, then the process zone, and other things. So we were able to even estimate the fracture properties of cement stabilized rammed earth. This is the DIC and the experimental load CMOD curve. The DIC, which was digital image correlation, it very well, we were able to get matching results of the two different ways in which we were able to get the load versus CMOD of the specimens. Now, this is how it's a video, but unfortunately, it is not playing. My DIC as well as the acoustic emission sensor, how it shows the damage being propagated. I cannot show you, unfortunately, video does not work. Thank you very much for your patient hearing. And I am always like to put up the picture of Sir M. Vishwesvaraya, the name of your institute. He is my hero. Nature never excuses lapses. Thank you very much. Now it's open for discussion.
Thank you so much, sir, for such an informative session.
Can we have discussion session?
Thank you so much, sir. Now, dear participants, the session is open for question and answer session. You can ask your questions now. You can also post the questions in the chat box. Okay, now I want to take a moment to extend my heartfelt gratitude to our esteemed speaker who shared his expertise on the fascinating topic of Earth as a building material, history, properties and engineering behavior during our faculty development program. His insightful presentation shed a light on the rich history, unique properties, and intricate engineering behavior of Earth as a sustainable building material. His knowledge and passion ignited our curiosity and opened our minds to new possibility in construction and architecture. Sir, we are truly grateful for your dedication to spreading awareness and deepening our understanding of environmentally friendly building practices. Your expertise has undoubtedly enriched our professional development and will continue to inspire us in our academic and professional pursuits. Thank you once again for your exceptional talk, for your invaluable contribution to our faculty development program. We look forward to applying insights gained from the presentation to our work and end use in the future. Thank you once again, sir.
Yeah, there is a question
Sir,
here.
there
It
are
says,
some
what is the
questions
reason
in
behind
the
wall
chat
collapse?
box.
One person posted here.
There is a question. What is the reason behind the wall collapse, sir?
Yeah, see, that was out of plane failure. I hope he is asking the question with relation to the building model. That was an out of plane failure.
Sir, I request you to kindly unmute yourself. I think now it's audible. So, can you hear me, sir?
You're asking me to mute my thing or what?
There's a small question. That's a reason behind the wall collapse. There is a question.
Yeah,
in the chat.
No, are you able to hear me?
Yeah, sir, yes.
Yeah, it is actually the building model. If he is referring to the building model test on shock table, it was out of plane flexural failure. That was the reason for the wall to collapse. That is one of the modes in which not only rammed earth, even our reinforced masonry walls, in the event of an earthquake, they fall when the load is out of plane. That is the weakest thing that can happen in buildings. So out of plane collapse of the walls due to flexion, bending.
Thank you, sir. I hope Mr. Raki, your question is answered.
Yeah, how can we prevent it? He is saying the only way you can prevent it is to reinforce the things. These are all unreinforced. You will have to reinforce it. I did mention to you when we are ramming the whole thing, you'll have to provide some kind of like reinforced concrete. You may have to provide some kind of other elements in the vertical direction and then put it in place and ram the soil. Then the soil, that rammed earth becomes reinforced rammed earth. Then you can prevent these kinds of out of plane flexural failure. Okay.
So by giving stiffer bond at every 1 meter.
Also it's possible where wall thickness can be increased. Okay.
Any more questions from the audience? Any more questions? Thank you, sir.
Thank you.
It was an innovative talk. Thank you, sir, for all your kind.
Thank you. Thank you.
Thank you, sir. I'll get in touch with you, sir.
Sure, sir. Sure. So if there are no more questions, can I leave the meeting?
Any more? Okay, sir. Thank you. Thanks a lot, sir. I think.
Thank you. All the best. Thank you very much to all of you. Thank you.
Sir, one more small question is there.